plan for today. We'll start by doing a little recap of what we did at the end of last class. So talking about converting from degrees to radians and about this relationship between angle and radians and arc length and radius. We'll pause there. We'll do like a 10-minute classwork assignment on the Delta Math. Come back together, talk about angles in standard position. We'll talk about what that means, how to draw them. Pause. Second classwork assignment in Delta Math, we'll practice that skill. And then that'll kind of complete things for today. So we're wrapping up section. We've done section 4.2. That was like the right triangle trig stuff. We'll finish section 4.1 today to start. And then we'll dip our toe into section 4.3 next time. We probably have 2 more classes today in section 4.3 before we're done. Okey dokes. All right. So. So we're just going to practice again how to convert from degrees to radians here to start. When we're converting from degrees to radians, the key thing to remember is the conversion factor. Who remembers the conversion factor? Body? Okay, that's the part of our definition for a radian angle measure, or an angle in radians. 180 degrees is equal to 1 pi, right? That's the conversion factor. That's the key thing to remember. Again, if you struggle to remember that, where could it go? On your half sheet for the test. So if you've got a sheet going for that, that would be something I'd recommend to kind of add. So if you're making your sheet kind of as you go, that would be a good thing to put on there, that 180 degrees is equal to pi radians. All right. So I suggested to think about doing these conversion problems like a unit conversion problem from a science class. So I'm going to think about 210 degrees over 1. So my conversion factor that I'm going to multiply by, where does the degree symbol go? Top or bottom? It should go on bottom, right? The units should be diagonal from each other. So degrees are on top on there. So in my conversion factor, the degree needs to go on bottom. So that means that we'll have pi radians on top. Everybody's okay? So if I multiply straight across, I have, actually, we'll do this first. So degrees cancels with degrees, so the unit we're left in is radians. If I multiply straight across, I'd have 210 pi over 180, right? The issue is that I want to reduce that fraction. So I'm going to reduce here before I multiply. Is that okay? All right. So if I look at 210 and 180, it should be real easy to see that, like, both of these things have a factor of 10 in there. I can just cross the zeros out. Everybody's okay there? And then if I look at 21 and 18, does anybody notice the common factor between those? 3, okay. So 3 goes into 18, and 3 goes into 21. So if I multiply across, we have 7 pi over 6 radians. Is everybody okay with that? Now, typically, for a degrees problem, going from degrees to radians, we'll want to report our answer as a fraction with pi in it. That's pretty standard. I mean, on occasion, maybe you prefer decimal here, but almost always I'll ask for our answer as a fraction in terms of pi on this kind of a problem. So you do need to be able to reduce the fraction. if you're like, ooh, fractions are a problem, Mr. Kulik, my suggestion is you just use your calculator. You do like the horizontal fraction bar, 210 over 180, press enter, and it'll spit out the reduced fraction. You just have to put the pi in. You know what I'm saying, or no? If the answer is no, you should say something. We can show you how to do this again.
Can I see it again, please?
Sure. Come on. Oh, fine. Yes, cookies. All right. So I do alpha and the variable. And I'm just going to type 210 over 180, press enter. And it gives me the reduced fraction. So all I have to do is remember to put the pi back in and write 7 pi over 6 instead of 7 over 6. But you can't put the pi in there, the calculator won't produce it. That. So you have to leave it off, do the fraction and put it back.
Right, okay, thank you.
Yep. So again, it should be easy, right? Just do you remember how to use the calculator to do that? All right. The other, now let's do the other way. We'll start with something in radians and end up with degrees. If your radian measure doesn't have a pi in it, like if it's just 2 radians or something, your degree answer will be a decimal that you can round. If your answer, or if your radian measure has a pi in it, it should reduce down to like a, rational number degrees. Okay. So let's say we have, I don't know, like 3 pi over 5 radians. So here, where's the radian unit located?
On the top.
At the top. So when I write my conversion factor, where do the radians have to go? On the bottom. So we'll put pi radians on the bottom and 180 degrees on top. So units of radians cancel. And I noticed something else. Oh Boise. Something else nice that's going to cancel. Those pi's are going to cancel, right? And then we should try to reduce the fraction. Right? We have 3 times 180 over 5. I'm going to reduce before multiplying. So obviously 3 and 5 have no common factors. Those are both prime numbers. But 5 and 180 certainly do. I know because 180 ends in a 0 or 5. I know it's divisible by 5. So I know 40 times 5 is 200, right? This is 20 less than 200. So it should be 18, right? Or sorry, 16. 5 goes into 180 16 times. Again, if you can't mental math it, that's why the calculator's there. Like, that's okay.
Should be 16 degrees still.
So, well, we still have 3 times 16. So my answer there should be 48 degrees. Cool with that, Tina?
Yes, Mr. Kulik.
Awesome. I said your name specifically.
Oh,
You didn't
oh,
answer, so I just
oh,
pretended that was
sorry,
your.
sorry.
It's okay. I'm just having fun.
Okay.
Right.
Yes, I got it.
Okay. All right. Everybody feel okay doing this process? Not bad, right? We're just talking about a unit conversion. It just, do I multiply by pi over 180 or 180 over pi? But it's going to be one or the other every time.
Is it 5 times 16?
It's 3 times 16.
No, I'm saying when you said how many times can 180 go in 5, is it 4, 16?
Oh, is it? Yeah, 36, right?
Yeah.
My goodness, Mr. Kulik. Okay, stop misbehaving, board. 36. Thank you. That makes a big ding dong difference, doesn't it, right?
Oh, yeah.
So what's that, 178? No,
108.
thank you. Mental math is hard at the end of the day, you know, like,
I agree. Math is hard all times. of the
All
day,
times of
so
the day.
I get what you mean.
it's hardest at the end of the day though, right? And Paula thought that was just the funniest thing ever. That's okay. Paul, are you like the designated laugher? Like every class has like one person that like no matter how bad the joke is, this kid's gonna laugh like it's the funniest thing ever. Is that you? I'm finding this stuff out, right? Everyone's shaking their head like, yeah, that's Paula. Okay, good to know.
I was just talking about something else apparently.
Okay. Now that we cleaned up all my arithmetic mistakes, goodness gracious, Mr. Kulik, let's kind of step forward and kind of finish out section 4.1 here. Okay?
Yes.
So last time we had talked about, where did you go? This formula right here. That we said that an angle measure in radians is equal to arc length over radius. So what I'm going to do is I'm going to call angle measure in radian. I'm going to abbreviate that as the Greek letter theta. I'm going to put an R subscript on that to remind me that that angle measure needs to be in radians. That's why I put the R there.
That's for angle measure, or that's for radians?
Angle measure in radians.
Oh,
So the
in
angle
radians.
measure is the theta. The R tells us
Okay.
radians. Everybody's okay? I'm going to use the letter S for arc length and the letter R for radius. So this formula I could write then as that. And most of us don't love fractions. So let's multiply both sides by R. Actually, let's write it in the opposite order. Be cleaner looking. So I can say that S is equal to radius times angle measure in radius. Is everybody okay? All I did was rearrange the formula that we had stated before. So that the angle measure is, or so that the arc length is by itself as opposed to the angle measure. No big deal, right?
Yes.
What happens if I have an angle in degrees instead of radians? And I want to use this formula. What am I going to have to do first? Convert it to radians, right? So if this is an angle in degrees, I have to have degrees on bottom and radians on top, right? And the output for this will be an angle in radians. Everybody's okay with that? So as an alternative to this formula then, I can take the angle measure in radians and write it as an angle measure in degrees, provided that I multiply by that conversion factor. So as a separate formula that'll accomplish the same thing, I could write that. So again, stay. Ugh, you little. Do what I tell you to. There. So again, same formula is accomplishing the same thing, right? The difference is one formula I'm going to choose if my angle is in degrees. Now the other formula I choose if the angle I'm given is in radians. Is everybody okay? That's all this is, right? It's that same formula we built last time. I just rearranged it and created a second option that, what if your teacher's mean enough to give you an angle in degrees? I could do it as a two-step problem, convert it to radians and plug it back in here, or I could do it all in one step. It's the same thing, right? So if I scroll down, that's what these two are saying. I didn't focus on this because if you notice, they just called it theta in both places, and they hid that where the angles in degrees and radians. I like putting the subscript on the angle in the formula. I think that's a little cleaner than what they did there. Let's do a couple of examples. So again, I just buzzed right through that because we did it above. We don't need to do this. So here it asks us to find the perimeter of a 60-degree slice of pizza. When we use this word perimeter, what does perimeter mean? Just in your own words. What is a perimeter? What's that? Okay, we think for a second. I'm gonna open the door because it's a million degrees in my room right now. And it's much cooler in the hallway for some reason, so Nicole.
All around the object.
Yeah, it's like the distance around the object. Perfect. Lovely definition. So if I was going to write a formula for the perimeter of this figure, I'd have 7 plus s plus 7. Everybody feel good about what I wrote? Pretty easy, straightforward, right? So to find the perimeter, what I really need to do is find s. And once I have that, the perimeter is easy because you just add 3 numbers together. So I observe when I look at this that, like, hey, this slice is just some piece of a circle, right? So this angle here is a central angle. This side 7 is a radius, and this side s is an arc length. I have a formula to find s given the central angle and the radius, right? It's one of the 2 formulas I just gave. Which one of the 2 would I want? The radian one or the degree one?
Let's talk about the coordination.
Degrees. Why? They gave us an angle in degrees. Yes, right? So I'm going to use the degree version. So we have r. Oh, let's write it up, I guess. I don't know, whatever. It's those 3 things on top in some order. I don't remember what order I wrote them in before. They're multiplied, so does the order really matter? No. Okay, so if I fill these in, my radius is 7. My angle in degrees is 60. And then I have my pi over 180. Everybody's okay? Degrees cancel. Let's reduce here. I notice that 60 goes into 180 3 times. Everybody's good there? I'm sorry. Yeah, 3 times. So I'm left with 7 pi over 3. So into my calculator, what I'll type is that, oops, and we'll round that to like 2 decimal places or something. Is everybody okay with what I did? So I started by writing my formula for perimeter. There's one piece that I needed to still solve for, and then I used my equation that we quoted before to solve for that missing piece and drop that answer into the formula I wrote at the very start. Let's type this in. So I have 7 plus 7 pi over 3 plus 7. So the answer I'll report is 21.3. Just round to 2 decimal places seems appropriate then. Now remember, this is a perimeter, so it's a length. So it should have some kind of unit attached to it. What will the unit here be?
Yeah, inches.
Inches. Very good. How'd you know it was inches? Because the length in the problem was given to us in inches. Just reading comprehension there, right? So far, so good? Everybody feel good about what we just did? Not too bad, right? I hope. All right, let's look at the last one here I got for you guys. This says the running lanes at the Emory Sears track at Bluffton College are 1 meter wide. The inside radius of lane 1 is 33 meters. The inside radius of lane 2 is 34 meters. How much longer is lane 2 than lane 1 around one turn? So, if you are running on a track and you want to get from the start to the finish as fast as you can and you're running along the curve, what part of the lane do you want to run on? Like the inside of the curve, right? That'll be the shortest distance. Everybody agree? Okay. So the inside lane or the inside part of lane 1 would be this distance. I'm going to call that S1. Everybody okay? And it wants us to compare that with the shortest distance it would take in lane 2. Call that S2. Everybody okay? And now it asks how much longer is lane 2 than lane 1? So what I'm going to be looking for is that distance S2 minus that distance S1. Is everybody okay how I just kind of started with what is this question asking for? Gave the two pieces that I needed to answer that question some names. And now I'm going to go through and try to figure out how to find the number of those two missing pieces. Right? Everybody's okay? Okay. So when I look at this picture, I say, ah, these look like parts of a circle, right? So if I was going to draw this, like the center would be here. And I have like that. Everybody agree? So this is like a central angle. And then this is like the radius for the red circle. Again, that was going to be the circle that I've designated as circle 1. Now, grab the thing I want. There. Stop bothering me. Is everybody okay? If I do the same thing for the blue circle, what do you notice about the angle theta there? It's the same angle. Everybody agree? Looking at this picture, what is the size of that angle? 180 degrees. How did you know that? That's perfect.
It's a half circle.
It's half of a circle. Everybody agree? Okay. So that's theta in degrees. If I want to write that as theta in radians, it's the easiest unit conversion problem you can ever be, well, second easiest you could ever be assigned. 0 is the easiest. What is this angle in radians? Pi, right? Because we know 180 degrees is pi radians. So if you had thought about it that way, that would be okay also. Is everybody okay? Still doing good? Does it matter which one I use? No. I just have to make sure whichever one I choose to use, I use the appropriate formula to go with it. Okay? So, if I look at my two formulas for arc length that we quoted back here, where did they go? They're up here. Yeah, there you are. Which one is simpler to use? Which one has less going on? The radiant one, right? So that's what I'm going to choose to use. I'm going to use my theta in radians because the formula to find the arc length, the S in my picture, is simpler to use. Since I have access to both degree and radian measure for the angle, and that was really easy to get, I'm just going to go ahead and use the arc or the radian version, just because it's simple. Everybody's okay? Will I get the same answer if I did it using degrees? Yes. Yes, I will. All right, where were we? Down here. Okay. So we're going to say S1 is equal to R1 theta, and S2 is equal to R2 theta. So R1 was 33 degrees, and theta R was pi. R2 is 34. Did I say 33 degrees? That's confusing. It's not. It's meters is the unit there. Good gravy. And theta R is still pi. So if I take those and plug them in, I have 34 pi minus 33 pi. Everybody okay? Now, you could type that in your calculator and press enter, but I don't need to do that. 34 pi minus 33 pi is 1 pi, right? Just like 33 or 34x minus 33x would just be 1x. So my answer is just pi meters. Or you could say 3.14 meters. Rounded to 2 decimal places. Sure. Go ahead and do that. That's okay. Do you feel okay on how we came to the answer on this story problem? Again, the hardest part was the very first step where I decided what it was that I needed to answer the question and identified the parts in my picture that were going to give me, that I needed in order to answer the question. Once I had everything identified, this was probably relatively easy because all you're doing is plugging stuff into formulas, right? The hardest part was translating from the words into this piece that kind of gave us a clue as to what do I need to do to solve this problem. Is everybody okay? When you run into a story problem, you need to read it until you can visualize what's going on, especially in a case like this where it's talking about like a physical situation. You should ask yourself, okay, what is the question that's being asked? What do I need to find? Relate the thing that you need to find in terms of variables, and then go about finding the value for those variables in order to answer the question. That's typically what you need to do. Okay? Is that reminder okay? So again, typically any story problem is not going to be that complicated once you understand what you're reading. Right? Okay, we're going to pause here. Work assignment on Delta Math for the 4-3 classwork. And if you need to finish up what this 4-1 classwork, you can do that first. If you have to finish at home, you have to finish at home because, quite frankly, there's no way for me to collect the Delta Math and keep it running. Like, you have it, you can do whatever you need to. So. All right. So, what we're going to first start talking about here in section 4.3 is I've hinted at this idea that like we can have these angles that are bigger than 180 and less than 0, right? It's possible to draw these angles, not in geometry the way we define an angle, but it's somehow going to be possible to do this, that these have meaning for us. So that's what we're going to be doing today, is talking about how to do this. So you remember, if we draw an angle in geometry like this, we always measure the smaller angle. So we measure it this way, but never this way. Everybody's okay? So we're stuck. Like, the biggest angle we can draw in geometry is 180 degrees. That's the straight line. So to work around that, we're going to come up with a new system to do this. So what we're going to do is we're going to take our angle, we're going to embed it in the xy axis. We're going to fix the vertex of our angle at the origin. That's the point 0, 0. We're going to take one arm of our angle and lay it on the positive x-axis. And then we're going to take the other arm of the angle, starting at the positive x-axis, and let it rotate degrees. So if it rotates 190 degrees, that'll represent a 190 degree angle. Is okay? So let's just kind of draw that, or give you an example of that, and do a little bit of vocab. So in my xy axis, I fix the vertex at the origin. One arm of my angle I lay on the positive x-axis. I call that the initial side. And then starting at that initial side, if I want, say, like 135 degree angle, I'm going to rotate. So one quadrant is how much? 90 degrees, right? Because it, like it's a right angle. And then half of a quadrant then should be 45, right? So if we do that, we've covered 135 degrees total. You guys agree? So this side then we would draw, and we call that guy the terminal side. Because that's like the end of our angle. It's where it terminates, it ends. Is everybody okay with this? So it seems pretty obvious now that I can draw angles much bigger than 180 now, right? Let's do another one, yeah? What would it look like if I tried to draw an angle bigger than 360? What's gonna happen there? Well, let's do an example. So I started out drawing my xy axis. I'm going to fix my vertex at the origin. I'm going to lay my initial side on the positive x-axis. This is the start for every single time we draw an angle. Vertex at the origin. Initial side on the positive x-axis. And now, I'm going to rotate my terminal side. So I'll have 90, 180, 270, 360, and then how much more do I have to go past 360? 45 more. So when I draw this, I've gone around one full time and then gone 45 more. Is everybody okay with what I did there? And now you see, okay, great. I can draw an angle as big as you want, Mr. Kulik. I might have to spin around this a couple of times, but like, whatevs, no big deal. When you guys are drawing your pictures, I want to see the spiral on your paper. I want to see which way you're rotating, how many times around you've gone. Okay? Now, when I drew my terminal side in here, did I know it was exactly 45 degrees that I went to get to there? What did I do? I just estimated, right? So here's what I'm looking for my estimation. I want your terminal side If it's closer to one than the other, it looks like it. So if it's 10 degrees past, it should be closer to this end, right? If it's 80 degrees past, it should be closer to this end. If it's kind of in the middle, it should look like it's kind of in the middle. But I'm not going to be like getting out a protractor being like, oh, you know, it just has to be close enough, right? So if it's closer to one axis than the other, it should look like that. Or if it should be kind of in the middle, it should look kind of in the middle. That's all I'm looking for. Okay? So here we go. I can do angles as big as I want, right? We also hinted that there was negative angles. Probably some of us ran into negative angle written in your delta math here just a moment ago. What am I going to do with a negative angle? Yeah, I'm going to rotate the other way. That's exactly right. So, positive angles. We're going to turn to the left. We're going to go counterclockwise. Negative angles. We're going to turn to the right and go clockwise. Everybody's okay with that? So now what can we do? I can now draw an angle as big as you want or as small as you want, Mr. Kulik. Makes no difference to me. Oh, we did this already. So this is just up here. Right? We talked about drawing an angle bigger than 360 already. I was out of order. Sorry, guys. That happens. Okay. Here's a little experiment for us. Let's draw a 120 degree angle and a 480 degree angle. And we're going to draw them on the same set of axes. And just kind of look at the picture of what happens, okay? So I'm going to use two colors. I'm going to do red and blue, just so it's easy to tell them apart when we look at it. So there's my axes. What do I start with? Vertex at the origin. Initial side on the positive x-axis. And then I'm going to rotate starting at that positive x-axis counterclockwise because it's a positive angle. I'm going to go 120 degrees. So 90 and then like 30 more. Is everybody okay with how I drew my 120 degree angle? Notice that I know 30 degrees is less than halfway, and it looks like that terminal side is less than halfway. Right? That's all I'm looking for in terms of accuracy. It doesn't have to actually be 30 degrees. You know, just has to be close. All right, let's do the 480 now. So again, vertex at the origin. Initial side on the positive x-axis. It's a positive angle, so I'm turning counterclockwise. So 90, 180, 270, 360, 450, and then 30 more. Oh my gosh, guys. Somebody's blowing up. And again, you don't have to write these 90s and stuff in there. I'm just writing that so you can see how I counted this out. Now, look at this picture. If I remove the spirals, what would you say about these two angles? They're the same. They're identical, right? If I took out the spiral, you would not be able to tell the difference between them. This has a special name in this instance. These two angles are called coterminal because they're terminal sides coincide. They share the exact same location. So in a way, even though these angles are different values, one is 120 degrees, the other is 480 degrees, they're going to behave the exact same way, because if I look at their picture, they look exactly the same, right? The way to kind of think about this in your mind is these things are going to behave kind of like equivalent fractions behave. Like 1/2 and 2/4 are the same, right? They both are 0.5, even though one of them has a denominator of 2 and one of them has a denominator of 4. If I was trying to add like 1/8, I would need to use the version of 1/2 that has a denominator of 8 to it. So in this kind of the same way, we'll be able to like reduce these angles, like a 480 degree angle, we'd probably just rather use the 120 by reducing it down, kind of in a similar fashion. We'll get more to that when we get a little bit further on, but I want to just plant that seed because we'll water it, put some sun on it, and harvest that idea later. Okay. So my question is, how many angles are going to be coterminal to a given angle? Say, let's talk about a 30 degree here. If I have a 30 degree angle, how many angles are coterminal to that one? Okay, too much time. Let's point something else out then. Let's go back to this picture. We'll sit on that for a moment. If I look at the 480 and 120, look at those two numbers. Do you see anything interesting when you compare those two numbers? Price was 4. Okay, one is 4 times the other. That's true, but that's not what I'm looking for. There's another important relationship going on between these two numbers. Body.
480 is a multiple 120.
Okay, that's the same thing as being like 1 is 4 times the other, right? That's okay. Band in 0, sure, but that's not what I'm looking for. Olivia?
360.
Their difference is 360 degrees. What's important about 360 degrees? It's one full time around, right? 420 is really, 360 plus 120. It's one full time around and then a 120 degree angle, right? So if I wanted another angle that was coterminal to 120, what could I do? Instead of going around just one time, I could go around 2 times, or 3, or 4, or 5. And how many angles are going to be coterminal to 120? Infinitely many, right? Because you can just keep going around and around and around as many times as you want, just ending at 120. Now, do I have to be going around in the counterclockwise direction? Nope. What else could I do? I could go around in the in the clockwise direction, right? So if I want to generate angles that are coterminal, what am I going to be doing? Adding 360 or subtracting 360. That's the whole idea. Is everybody okay there? Okay. Infinitely many. Right. That was our answer. We're going to stop here. I don't want to deal with radians yet today doing this. This is a good place to stop. We're going to do the classwork for 4.3, but I want to show you on the Delta Math how to use the Delta Math to do it. Because what we're going to be doing on that Delta Math is drawing these angles or estimating the value. So let's do this. That one.
We're jumping around.
4.3 classwork. That one. Okay. So 4.3 classwork 1. I guess it's now past due. I'm sorry about that, guys. It's fine. You're not going to be graded down on that. Still do it. All right. The first type of question asks us to estimate the angle within 10 degrees. So here they've drawn us our angle. If I look at this, it looks like it is in quadrant 1. So it's between 0 and 90, right? Where's that terminal side between 0 and 90? Looks like about halfway to me, right? So this angle is probably pretty close to 45 degrees. That's what I'm going to do as my guess. I don't have to be dead on. We just have to be within 10 degrees either way. And they said close enough. The actual angle was 41 degrees, but I was within my 10-degree window, so it's correct. Everybody feel okay on doing this?
Yeah.
That's one set of problems, just estimating what the size of the angle is. The next one is rotating small angles. So this is going to be drawing these angles. And by the way, this method of drawing angles is called standard position. So we're going to be drawing a standard position angle. And it says 12 degrees within 10 degrees. So I know it's going counterclockwise because it's positive. It's just a tick over the x-axis. That should be good enough. Submit my answer. And it says yes. Let's see, my answer was 4 degrees. The actual answer was, what I was supposed to get was 12, but it was good enough. Do another one that's not quite so trivial. Negative 18 degrees. Which way am I going this time? Clockwise. So maybe, I don't know, there. 18 is about 2/9 of 90 degrees, right? It's like, so if I look about this, like, that's probably pretty close. I like to try to divide it into fractions. Said it was close enough. My answer was negative 15, so I was within 4. Good enough. If I look at the last set, this is large angles, so that means you're going to have more than one trip around the unit or around the circle. So here we have negative 645. So I'm going to start going clockwise. So I have negative 90, negative 180, negative 270, negative 360, negative 450, negative 540, negative 630, and then like 24 more. So maybe about there. And that's good. So what does it say? What was my answer? Negative 652. So I was within 2 degrees that time. Pretty good. You can stand up and do a little dance if you get it spot on. Everybody cool? And what to do? Fairly straightforward, right? And this makes it easy because some of us, neatness is not our strength. Here, the computer takes care of all the neatness for us, so you can handle it pretty easily. Everybody cool?
Yes.
All right. Get crack-a-lack, and if you finish this and you still had the 4-1 classwork for today to finish, you can finish that before you start, or you can just dive right into this one. This is what we're doing for the rest of the time, so once you finish this stuff, you are done for today. Everybody cool? Absolutely. Grab a pass off the bulletin board there. You guys happy? This one okay today? Yeah? You're like, when's the math gonna start mathing? I know it's gonna get scary here eventually, but so far this hopefully has been fairly okay. And today was mostly just drawing pictures. It's cool, I love drawing pictures. Like, let's do that. It is a really important skill that you're able to draw these standard position angles accurately. It comes in, or it's a very necessary skill as we get further in, so you definitely will be well rewarded if you get good at